All right, this is class number 3. It is Thursday, April 4th, 2024. And finally, I have a chance, I think, to make a good presentation on the history of temperature. And that's going to break down into 3 parts. That's going to be galactic drivers of temperature, orbital drivers, and solar drivers. And that's what we're going to go through now. We've already had the 4.5 billion year history, and now we're kind of zeroing in on the last, 5 million years and up. And remember that at 14 million years ago, the Isthmus of Panama closed, and before that, at 33 million years ago, we had the Saudi Arabian Peninsula close the Mediterranean off, and that really began the Ice Age. So we've been in an ice age for at least 14 million years. We don't really come out of it. We have interglacials and glacials, and that's what we're going to be looking at today. We're essentially still in an ice age because we have ice at the polar caps year round. And that's not going to change until the continents allow more heat to build up and not escape, right? We're all pretty familiar with that. So let's go. Back to our world of temperature. And the key here is that the driver of temperature depends on the time window, on the length of time you're looking at. So here's 5 million years. And the first thing we notice is that temperatures have gone down a little bit over the last 5 million years. And right about 1.2 million years ago, there was this mid-Pleistocene transition. I should probably label it, but that's what this is about. Mid-Pleistocene transition. Before that, the driver was mostly obliquity. This is mostly a 41,000 year period. And after that, eccentricity has really come onto the scene and shown itself to be a strong driver. So if we zoom into the 1 million, and this is about the resolution of most ice cores. I think the deepest ice core is the Vostok, and it gives us about 3 million years. And most of the ice cores go to about 1 million, 1.5 million years. And so this is ice core data. And it shows that right here in the mid-Pleistocene transition, we went to this more 100,000 year peak regime. And it's really driven, as we saw, by eccentricity. I'm reviewing this because it's all going to stack up over the next 45 minutes, okay? Recall that from a point of view of eccentricity, which is the roundness or the eccentricness, the ovalness of the Earth's orbit, it goes in waves, just like at the beach. Waves come in waves, and there's a big peak, and then we're going actually forward this way. It goes down, and then there's a big peak again. And those waves typically correspond with high, let's call them interglacials. These are called interglacials. I'm going to use my handy pink. Oh, did I turn that off? I'm going to use my handy pink tool here to show that these are the interglacials. Got to organize myself. Did I admit? Yeah. Okay. So these are, anywhere around here. This is above this. This is an interglacial. And then below that is really cold. We've been in an ice age for 14 million years. And it's cold, and then these are called down here are called the glacials. And this is where you get miles of ice over London, St. Petersburg, New York, Toronto. And, humans have been through a couple of these. Well, one of them really. This is our last ice age here. Actually, this is our last ice age here, and this is our last big maximum. So we're not going to look at this resolution here. We're just going to look overall, and we're going to look at how eccentricity generally forms peaks. Okay, for example, this little peak, it's not very influential, but it sends temperatures up as it peaks. There's obviously other things going on because you can see that temperature is going down as obliquity is going up. Remember that obliquity is the ovalness, and the more oval it is, the more extreme things are. And that means that when the Earth is near the sun, comes near the sun, it has more chance to beat back the ice. The ice is always trying to form. We're in an ice age. The ice is trying to form, and when you have a longer summer or a hotter summer, you can beat back the ice. And if you have 500 of those summers or 1,000 or 10,000 of those summers in a row, you can really melt the glaciers. And there's a lot of other things involved, but that's very important that the more eccentric, the warmer, because we can, even though the winters are colder, the summers have more of a chance to beat back the ice. Okay, so mostly these eccentric times coincide with low ice or interglacials, with the glaciers retreating. And when we have very round conditions, especially down here where the orbit is very round, we tend to have ice. Now, it's not perfect, and we're going to get to that. In fact, this is before the mid-Pleistocene transition. So you can already see this isn't very influential. Why? Why is eccentricity not very influential before and then it is afterwards? Nobody knows. There's a lot of debate about it. Well, there's a small amount of debate about it because there's only 10 people in the world who really care. But there's a little bit of a debate and it's a mystery. All right. But now you can see it starts to kick in. And when we have low eccentricity, we tend to have a lot of ice. Okay, low eccentricity generally means a lot of ice. That means more round. It means the summer doesn't have a chance to beat back the ice. Now we're going to go to obliquity. I'm going to bring in the 41,000 year. So eccentricity is a 100,000 year cycle with a 405,000 year supercycle. Okay. And obliquity is a 41,000 year cycle. And what's to notice here is that obliquity. What is obliquity? It's the tilt from about 21 degrees to 24.5 degrees, something like that. Okay, it's the Earth is never straight up and down relative to the sun's equator. It's always tilted. But we have less tilt and more tilt. When there's more tilt, that's higher obliquity. More obliquity, there's longer summers, and the sun has a chance to beat back the ice. We'll put Europe here. Okay, the sun has a chance to the glaciers retreat because the summer pushes every year a little ice back, and then when we have lower obliquity, the glaciers come down. Takes 1,000 or 5,000 years, but the glaciers come down when those extra days of summer are gone. Okay, because the ice wants to form, contrary to what politicians think. We live in cold times. Here are the key takeaways from obliquity. It's every 41,000 years. And when obliquity goes up, generally temperature rises. When obliquity goes up, generally we can see temperature going up. Here's a little one that's a bit of an exception, right? Generally, when obliquity goes up, temperature rises. Another exception. This is called a missing beat. When obliquity goes up, temperature goes up. Okay. And then we also notice that when obliquity goes down, temperature goes down. And this is an even stronger correlation. When obliquity goes down, temperature down. Obliquity down, temperature down. This has fewer exceptions. It's almost always the case that as we go more towards straight up, we get more ice. We go more into a glacial period. Even here, you can see the beat missed, But as we go down in obliquity, we go down in temperature. See that? So the downward correlation is stronger, right? And if you look at it, kind of step back and squint a little bit, you can see that we tend to go up faster and down slower. Generally up fast and down slow, and that has to do with feedbacks and how the ice forms. And so obliquity is a pretty good measuring stick to say when we're going more towards straight up, temperatures drop. Here's another missing beat where it went up in obliquity, but not in temperature. But sure enough, when obliquity goes down, temperature goes down. And here we're caught up and and this is because there's other factors at play. And so, if anybody who says, oh, that orbital mechanics stuff, that doesn't work. Well, it works 85% of the time. That's relevant. So we keep that in mind, but there are other things going on. And now we have precession, and I want to clear up a confusion about precession. What's precession? Precession is the 26,000 year cycle of the Earth's North Pole moving around the zodiac. In the north sky right now we have Polaris is our North Star. But even the Greeks 2,000 years ago knew that the North Star changed over time because of stories of which star is north, and it's after 5,000 or 6,000 years, it's no longer north. It moves in a circle. So if you think of the circles up there, of the stars up there, if you sort of choose a bunch of stars that are in a circle, every 500 years, we go to the next star. Or every 1,000 years, we go to the next star. So right now, Polaris is north. But this precession cycle is just like a wobble on a top or a gyroscope, is very regular. It's 26,000 years like clockwork. All it really does is change the seasons. So now we're going to bring this back, and I'm going to explain this again. This is a little tricky. So in fact, I'm going to make myself bigger for this. Am I bigger? We have the tilt isn't changing right now, and on the order of 6,000 years, the tilt doesn't change much. Okay, but on the order of 6,000 years, the North Star changes. So right now and I don't like the word summer because summer is different 6,000 years from now. So I'm going to use July. In July, the northern hemisphere the Earth is farthest from the sun. This is a 3 million mile radius difference between July and January. 3 million miles out of 93 million. So, it's 3%. Okay. Here's July. Here is January. What it means is that Australians have very hot summers and very cold winters. So Australians get the extremes. And those of us in the northern hemisphere, here we are, we have okay, let me go back. Okay, so this is January. This is July. January, hot summer in Australia, cold winter or mild winter in northern hemisphere, hot summer in southern hemisphere, mild winter in colder winter in the south, hotter summer in the south, colder winter in the south in July. Their extremes are more extreme. In the north, it's the same thing, but we have the mild conditions because in July, we're farther. In January, we're closer, which means we have a milder winter, milder summer, milder winter in the north. In the south, a much colder winter and a warmer summer. Now, I'm going to throw in precession. Come back in half of 21,000 years, which is, 11,000 something or 10,000 something. And it's the opposite. Now this is January. So in 10,000 years, January is the summer. In 10,000 years, July, did I say January? Yeah, this is January and this is July. In 10,000 years, it's the opposite. This is January and this is July. Now I can do it a different way so it might be less confusing. This is right now. This is summer. This is winter for the north, summer for the north. If we change precession, this is what we get. The same angle, but it's turned around 180 degrees. Okay, so let's look at it that way. Okay, the sun hasn't moved. Okay, and in this case, this is still July. Okay, but in July, we have very cold winters up north, very cold winters up north in July, because the seasons are the opposite. Let me try to bring it here. Okay, so very cold winters, and then we have very hot summers. 10,000 years from now. In the north, we have very cold winters. We have the extremes. 10,000 years from now, we have the extremes. And the Australians have a milder summer and a milder winter in 10,000 years. Does that make sense? That's half, because the Earth has made half of a wobble. Okay, now we'll go back to the present day, which is like this. And we have mild, in the north, we have milder seasons. We have milder, here's Europe again. We have milder summers and milder winters. But there's a catch. Because we're 3 million miles closer to the sun, we have about 7% more solar energy coming in January than we do in July. About 7% more. And yet, and this is really important, and yet the Earth is warmest when we're farther away in July. The entire Earth is warmest in July, and the entire Earth is coldest in January, and that's by 2.2 degrees Celsius. So anytime you hear about the 2-degree limit, well, we do that every 6 months. And it's the difference between our summer and our winter. Sure, it's 2.2 degrees Celsius. The Earth is warmest here where we have our mild summer. And the Earth is coldest here when we have our mild winter, and the Australians have a very hot summer. And what's going on? What's going on is we're closest to the sun here. There's more energy here, but it's mostly going into the oceans and then making its way to the South Pole and getting out without really, influencing the land temperatures, because there isn't much land down here. Whereas over here, when it's July, there's about twice as much land in the northern hemisphere. And so the land, again, has a chance to beat back the ice, and you get hotter temperatures at your thermometers. The land kind of drives that by absorbing more heat, and the oceans absorb less. So the entire planet, if you average it out, is hotter by 2.2 degrees in summer, even though we're farther away, in July, even though we're farther away, and colder by 2.2 degrees, even though we're 3 million miles closer in January. Is that confusing enough? If I repeat it enough, maybe it helps. It takes a little while to really get this. But precession just rotates the axis, and which star is the North Star? The North Star changes. So now to go back, Now back here, we often see precession that looks like this waveform here. It looks like, oh, there's more precession, there's less precession, more precession, less precession. This is nonsense. It's very common and it's not true, and I want to explain it. Precession looks like this. It's a sine wave. It's just rotation of the wobble of the axis. That's all it is. It can't have a dimension because there is no high precession or low precession. It's just, you know, the change of the seasons are a little different every, you know, rotation. It's just changing the seasons. So it's actually impossible to modulate this. It's just like clockwork every 26,000 years. Nothing really modulates. This, if you notice, corresponds to eccentricity. So we have the highest difference here, and then it goes down, and then it's minimum here, and then a little more, and then it grows. Okay, so this is precession modulating eccentricity. It's precession and eccentricity combined, and it doesn't make any sense. It's not good. It's not good representation of data. This doesn't represent the real world. It's very common, and I'm explaining it just because people think of it as, we call it the eccentricity index. It modifies, this is a 100,000 year cycle. It modifies that cycle on a 26,000 year basis. So whatever is driving in eccentricity gets modified by, and it's called the index because it's secondary. But it just makes no sense visually to do this. This is really precession. Precession just spins around and that's it. If you want to change the angle, you need obliquity. Obliquity does that on a 41,000 year. Okay. All right. So that is all pretty confusing. And I want to make sure that people, you know, pretty well understand this. So are there any questions to that? This is eccentricity, obliquity, and precession. Any questions?
I was thinking, if, say, right now in England, July is a hot summer, would that mean in 13,000 years it would be, July would be winter, or would it just
for
be...
sure. That's exactly right. In
so it reverses.
Years, in 13,000 years, it will be like this, essentially. And so your hot summers will come here. Or in 11,000 years, your hot summers will be here.
So summer would be in January.
And then your winters will be colder. So it'll be more extreme for the northern hemisphere, just as today it's more extreme for the southern hemisphere. They have hotter summers and colder winters.
Nice one.
Okay. Right now I've jumped ahead. Now I'm going to go back in time to talk about the galactic effects, and then I'll jump forward and talk about the sunspot. So I'm doing this in the wrong order. So the galactic effects going back millions and millions of years. If you look more like at the, you know, over the course of 1 billion years of Earth history, the sun is making its way around the center of the galaxy. So now we're recalibrating, we're erasing the whiteboard. Here, let me just come back here. Yeah. We're erasing the whiteboard now, and we're looking at 1 billion years. On the scale of 1 billion years, what drives temperature is interesting. Part of it is the way the solar system moves around the galaxy. So here's the galaxy. Remember, the galaxy is about 120,000 light years across. 120,000. And I've made a little model of our galaxy here. We've got the sun in the middle. Here's Earth, or Venus, Earth. I think that's Earth. And then here's Jupiter and Jupiter and Saturn. These are the big ones. And remember that the whole galaxy, the whole solar system works according to the barycenter. Everything rotates around the barycenter because everything's pulling everything else. And so the barycenter makes this little wobbling track that sometimes the barycenter, which is the center of mass of the galaxy, is sometimes inside the sun. And then sometimes if Jupiter and Saturn line up, it can pull the barycenter outside the sun. So it's a wobble, and it's a kind of a top-like shape that gets described as it goes around. Now, how do we move through the galaxy as a solar system? This is what I want to talk about next. First thing is, as we go around the galaxy, we're at an angle. So it's about a 60-degree angle. So right now the planets kind of lead at the bottom, and then 6 months later they trail the sun, and we're going around the galaxy at an angle. Okay, and in fact, you can see that I just made a mistake in doing this, because this is kind of intuitive that we would do this going around, but that's not what happens, because that doesn't conserve angular momentum. To conserve angular momentum, what really happens going around the galaxy is this. So this trip takes 230 million years. Once around the galaxy, 230 million years, about 4 times in a billion years. And we're going around right now facing what we would call forward if this is north. But when we have this class, or classes are conducted in about 60 million years, all the textbooks will say, and of course there won't be any humans in 60 million years, but all the textbooks will say, the galaxy is sliding sideways across. The solar system is gliding sideways across the galaxy. And then in another 60 million, 110 million years or so, all the textbooks will say, well, we're going backwards, or, the South Pole is the new north, or, it depends on who's talking. But in 120 million years, we'll be going this way. And then again, in another 60 million years, we're sliding sideways, preserving angular momentum. Couldn't be any other way. Okay, so this is the motion of the solar system around the galaxy every 230 million years. Now, as it turns out, the galaxy has spiral arms, 5, I forget. And as we go through the spiral arms, we encounter a lot more material, especially a lot more stellar material and a lot more cosmic rays. And we can actually see in the rocks a 150 million year signature that every time we pass through a spiral arm, on every 150 million years, we get more material to nucleate clouds, and it's cloudier as far as we can tell, and that changes the climate. And so there we have an influence of the galaxy on our climate going through the spiral arms. This is work by Nir Shaviv in Technion, Israel. And probably dark matter has something to do with this nucleation of clouds. That's all speculative, but it's possible that dark matter has something to do with our climate. And that would be at this point when the solar system is traveling through the spiral arms. Okay, not something too much to get into, but we can see it in the rocks, in the geology, that there's a 150 million year pattern. Now, the other thing is that the sun doesn't just go around the disk of the galaxy. No, the sun goes up and down through the disk of the galaxy, and it goes up and down on a periodicity of about 60 million years. So about every 30 million years, we pass through the disk of the galaxy. And another 30 million years, we pass through the disk of the galaxy and we're high. And then we pass through it again and we're low. And we pass through it again and we're high. Right now we're high if north is up. And we're about 300 light years above the plane of the galaxy. And that's not very far, because the bulging disk at the center of the galaxy is about 12,000 light years thick. So we're a little bit above the plane of the galaxy, but enough to, again, steer clear of some of that cosmic debris and the cosmic rays, which, as we go down through the plane of the galaxy, increase cloud nucleation. And remember, not only that can make shade, but it also increases the albedo. What's the albedo of the Earth? Who knows what the albedo is? Anybody? Albedo? Nobody? Albedo,
The
Tony?
reflectivity.
Reflectivity, how much of the incoming solar radiation bounces off the Earth when it hits something white. A lot of that's just going to get reflected, and that has no influence on our climate. It just goes away. It's just shining. Same as moonlight, you know, is reflected sunlight coming to Earth, coming to us. So more clouds and cloudiness can change the albedo, the reflectivity, which changes the energy balance of the Earth and can make things colder. Could also potentially make things warmer if it's more humid, but not very cloudy. So there is a 150 million year signature in the rocks. There is a 60 million year signature in the rocks. Has to do with cloud nucleation by cosmic rays as we go through various dense parts of the galaxy. Dark matter probably plays some role, and there's a lot of other stuff we don't understand. But this is just kind of first order, solar science. And those are the galactic effects, 150 and 60 million years. At a lower resolution of just millions of years, none of that plays any role because we're just not moving that much with respect to the galaxy. Okay, so in millions of years, we're talking more about the orbital effects that we discussed. And now I want to stay a bit with the orbital effects and go down into higher resolution of time. So the first thing we'll do is we'll take the last 200,000 years, which turns out to be pretty interesting, and we'll look at that. So I think everybody can see this. Here I've got the 3 precession, obliquity, and eccentricity. We'll just turn off those so we can see eccentricity. Over 200,000 years, we can see eccentricity doing a pretty good job. Remember, eccentricity means more chance to beat back the ice. It's more oval. And here it's more circular. And circular pulls temperatures down. And these temperatures are down. These temperatures are way down from up here. Okay? We're going in waves. This temperature here is very high. Okay, that's not within 200,000 years. All right. Then we have obliquity, which is 41,000 years. And you can see there's a pretty good correlation. When they both work together, temperatures go up. When they're not working together, temperatures can go up. And when they're both pretty much down, temperatures are down. Remember here we have fairly low obliquity, even though there's a little bump, it's still low obliquity, rounder. And then here as obliquity drops off, which means we're more upright, temperature drops off. And this is our last glacial period here at 23,000 years. It's our last glacial maximum. That you can see that. Sorry?
I don't think we're sharing your screen at the moment. I can't see it.
Can anybody see my screen? Yes.
Yeah, I can see it.
Everybody sees the screen, Barbara.
Oh, okay.
What do
It's
you
just
see?
me. All right.
You see it?
Black. Just black.
You just see black?
Yeah, don't worry. Don't worry. That's okay. You carry on.
Well,
I'll
it'll be on
try.
the video.
Yeah, yeah.
So I don't know. So here you can see what's driving at this resolution of 100, 200,000 years. Obliquity is driving. Do you see that? Everybody? Obliquity is really driving temperature at this time scale. Okay, there we go. All right, now we're going to go down to the last, this is called the Eocene, the last 100,000 years. Let me just zoom in here to the last glacial and show you that coming out of the last glacial period, it was very cold. Remember, this is the time when there was a mile of ice over Boston, 2 kilometers of ice over Montreal. Don't know how much over European cities, but kilometers probably. And then as obliquity, we started to get more angle, which gave a chance to beat back the ice in summer. We got longer summers, more summer exposure. The temperature started to climb. Here, sea level was 130 meters lower than today. And as a lot of ice, all the ice that was on top of New York and Boston and Montreal and London and Oslo has melted, it has risen 130 meters. In fact, probably a little more, and then came back down. And that's because temperatures went up a lot. You can see very jagged. And these are called the Younger Dryas. And this is advanced, but if you're interested in what's causing this, this is the Dansgaard-Oeschger events that go up and the Heinrich events that go down. Now, that's not going to be on the test, so don't worry. But now we get into the last 10,000 years, which is, look how stable temperature is for 10,000 years. It's kind of unprecedentedly stable, right? Which again means that you just can't predict from these orbital mechanics. There's a lot of other stuff going on. So now we look at 10,000 years. Everybody can see this, except maybe Barbara. Maybe Barbara, if you leave and come back. Try, if you see a black screen, you might as well try it. Well, you know what? Wait, I'll stop sharing and I'll start sharing again. Let's try that. Did that help? Can you see my screen? Can you see my screen now?
No, I'll go and come back.
Yeah, go out and come back. I'll let you back in. All right, so this is the last 10,000 years, and you can see that we're coming up out of that last, out of the Younger Dryas cold freeze, and we came out very quickly, very fast. Extreme temperature rise. So if people say that, temperatures are going up fast now, there's nothing compared to what was going on back here. And in other Dansgaard-Oeschger events, which we'll cover in another day. We'll cover some of these sudden events in another day. And Javier makes a big deal of them. Now we can divide this into two periods. This is called the Holocene climate optimum, the very warm period. When here there was mostly no ice at the North Pole in summer. Keep in mind that the South Pole is 2 miles thick of ice on a high plateau, and it's not going anywhere. It's not melting for probably a couple 100,000 years. There's just not going to make much of a dent in that. But here at the North Pole, there is no land. It's all ocean. It's a 2 mile deep ocean, and the ice is very thin. And here at this time, we have close to or somewhere around no ice in summer. And remember, polar bears were thriving during this entire time. They did fine. They didn't need any summer ice. That's because they don't feed in summer, but that's another story. But what I want you to see here is that temperature started to go down about 4,000 years ago, right? And whose fault is that? Well, look at this. I don't really have it here, but this is, I just want you to see, this is precession. This is precession. This is that 13,000 years ago was that extreme when the northern hemisphere has more sun, hotter. This is the precession driving at this resolution of 10,000 years. Here we have that situation I mentioned where it's like this. It's more extreme for the northern hemisphere, colder winters, but more chance to beat back the ice when we're nearby in January. So January was summertime here, and it was more chance to beat back the ice and have a hotter planet, and we did. It was several degrees hotter, and the ice was mostly gone from the Arctic in wintertime. Okay, and this is all precession. As we come around 180 degrees, temperatures fall because we're now in that more mild situation where the ice can't beat back as much. And so it's colder than it was back then at the climatic optimum. And this is caveman times. Caveman had it great. Caveman really, I don't know why they didn't invent the steam engine back here. To be honest, they had it really good. They were just slouching and I guess getting by, killing the the mastodons, and life was pretty good. They didn't have to do much more. Mastodons were easy to kill. So life is pretty good here. And then as we, even in the north, and this is, a time when there were grapes grown in England. Okay. And then as we come down, we all have to adjust to these more difficult conditions. And so let's go into that. This is 4,000 years. And here we can start to see how society or how civilization has been affected. I'm going to just bring it to 4,000 years here. And now, remember, now we're out of orbital mechanics, because precession has more or less done its thing, but at the level of 4,000 years, precession hasn't changed much. Okay, a little bit. The North Star has changed a bit, but not that much. And now we have sunspots. And so now we're going to go into the third part and talk about sunspots now. Okay, and there are many sunspot cycles. Oh, good. I'm going to talk about those in a second. So at the level of 4,000 years, what we see is temperatures have come down a lot from the optimum, and we see civilization grows as temperatures grow. This is all relative. Indian and Egyptian civilizations thrived, and then they collapsed. The Bronze Age is here, and it peaks with the Minoans. And then there was, if you're a student of history, there was a great drought down here. Terrible things happened on the way out of the Minoan. The end of the Bronze Age was not a good time to be born. 1300 BC, 1200 BC, very nasty conditions. Pirates, infighting, empires collapsing, freezing cold in some places, Shang Dynasty collapse, all empires collapse, anarchy, great craziness. And only until things start to get warmer do we get more civilization. And here's Alexander. Alexander the Great built the Macedonian Empire in a downturn of temperature, not a lot. It was still relatively going up, but his entire empire, and he took over the Persian Empire, was built here during this little downturn. Then the Romans really came and peaked as temperatures allowed. Think about it. If you're not at a subsistence level of shivering in the cold and trying to get potatoes out of the ground, you have a chance to have, more trade, more wealth, scholars, kings who had, astronomers, and, more science comes as we get more, warmer conditions, because we can afford it. And down when it's low, it's all subsistence and life is miserable. So here's the peak of the Roman Empire. And then boom, once again, and this is going to be driven by sunspots, and mostly sunspots, as we're going to see. Solar fluctuations. We lost the Roman Empire. Things went way down. This is called we're on our way down really sort of gradually to the Little Roman Ice Age. And that's, here for a little while, it's a little warmer, and we have the Vikings have farms. In Greenland, the late Roman period was pretty good. But now look, at about 400 and something AD, things start to tank, and the Roman Empire disintegrates. All of those northern outposts of the Romans, you think of the Germans, the Celts, the Gauls, all of those northern outposts that were paying tribute and sending tax money back to Rome, that all disappears. This all becomes, village to village ground fighting among small tribes that kicked the Romans out. And things again descended into the Dark Ages, when really what's happening here is religion is the only thing anybody's got to cling to, because science and progress stop when you get to subsistence level living, and you turn to the church because it's all you've got. And so these are the Dark Ages, not too surprisingly, coincided with very cold times, very cold. Famine, crime, the plague. The plague hit several times here and wiped out 1/10 of the world population several times in here. Then comes the Renaissance, and by 1,000 years, things were pretty good. Again, things are pretty warm, and vineyards are again flourishing in the UK here. There is still, I think, farming in Greenland here. And then again, because of, and we're going to see this in a minute, the Maunder minimum in sunspots, things go down and people are pissed. I mean, this is really no fun, the little ice age. It was only after this brutal period, 50,000 humans were killed, because you got to find a scapegoat. The church comes back with a vengeance when the weather turns cold. And the little ice age was just a disaster for science and progress. And only after that do we have the industrial era, as temperatures, we get some relief from the ice. So let's look at sunspots here. Oh, I'm sorry. I do have sunspots, I think. Let's see how the sunspot cycles affect this. So here's the Bray cycle, and this is 2,500 years. I should have turned this on before. This is the Bray cycle. Not here. Let me just, right there. Shows that when the Bray cycle is lower sunspots, this is the Maunder minimum. This was like no sunspots for 300 years. It's pretty unusual. And this can happen during the Bray cycle. This is more sunspots, better weather, fewer sunspots, worse weather. This is a 2,500 year cycle we can see in the rocks. And we actually have good records starting in about 1300. And then we have the Eddy cycle, which is that's 2,500. This is a 1,000 year cycle, the Eddy cycle. And you see when they work together, you get higher highs. So these two cycles, and these are sunspot cycles, so it's complex. Okay, but we see a 1,000 year periodicity in temperature, and we see a 2,500 year periodicity in temperature. And then showing that when they combine, it's cold. Okay, here are the two coming together and it's cold. And I can guarantee you the next time they're together, it's going to be cold. This just so happens right now, they're mostly working together to pull us out of that little ice age. So this is about 1750 that we started to get out. And we've been on this path since then. Coming out of the little ice age is our current warm period. Did not start in 1950 with some, smokestacks and tailpipe emissions. Now here we are in the last 600 years, and this is where we have really good sunspot records. We have, people keeping track of sunspots. And this shows that we can add the Feynman. This is from Joan Feynman, sister of Richard Feynman. She was a solar physicist, and she discovered a repeating pattern every 100 years, and it's pretty recent. It doesn't have much influence beyond about 500 years ago, but for the last 500 years, there has been some 100-year period. See, here's nothing. Some 100-year ups and downs that kind of correlate with temperature, although it's not great. And there are other temperature graphs that show a little better correlation. And now we get to what's called the Schwabe cycle. And this is the actual number of sunspots. And this is, you've probably heard of this. You've probably heard of this. I'm going to turn off that sunspots are in waves, come in groups, waves of sunspots, right? And we're what number sunspot group are we in right now? Sunspot cycle number 25. Right now, we're just getting to the peak of it. than most sunspots now. It's not predicted to be a much bigger. Pretty soon it's going to start to turn around and then it'll go down. And when it goes down, temperatures often go down. And when it goes up, temperatures often go up. But it's obviously not some kind of 100% correlation. It's kind of correlated. The main correlation is here when we had no sunspots for a couple hundred years. And that's called the Maunder minimum. And that probably had a huge influence and probably was the driver of the Little Ice Age. This is the Little Ice Age. Okay, coming out of the Little Ice Age now. And so this people talk a lot about sunspots. I don't think too much about sunspots. I do think it's part of the equation at this resolution of 100 years. You have to pay attention to sunspots, but I'm much more interested in ocean oscillations. And so we're going to go there in a couple of weeks. I just wanted to kind of get the sunspot stuff over with because as you can see, there is some correlation and it does have something to do with climate. Now we are reaching the last mile. This is the last 120, 140 years. And this is data that I've carefully constructed from the US and actually probably a lot of this is also just from the Global Historical Climatology Network. This is a bunch of stations, weather stations that have been keeping careful track of maximum and minimum temperatures every day for, here, somebody's in the chat, sir. 25. Oh, somebody said, Louise said 25. Right. Good. Every day since around the 1800s, 1900s, a lot of these people were the caretakers of railroad stations around the country. They were asked to install a weather station 6 feet above the ground and keep daily logbook records, writing with a pen and ink in a logbook. And so if you collect all those logbooks, and there are thousands of them, and there are thousands of families around the world who spent not just decades, but generations writing down max and min temperatures every day. So this is millions of data points to bring us something like this that you probably won't see if you look in the mainstream media, because they like to tilt this so that the 30s weren't very hot. And that's a lot of the data corruption that we face from government agencies like NASA and from extremist groups, I would say. They like to minimize the 30s, but the 30s were almost as hot as today, very close. And I'm going to show you that in a second. This network of people, humans taking temperature records lasted until 1979, at which point the satellites took off. And this is John Christie and Roy Spencer designed the instruments and then put them in the air. And these guys are still tracking temperatures. And we have the satellite era. And what happened in the satellite era was within about 15 years, almost all of these people stopped tracking temperature because they didn't have any incentive to anymore and it wasn't any fun. So this historical thermometer network stopped producing reliable data by 1985, 1990. It's useless after that. And so the NOAA continues the data so they can fabricate data and make it look warmer, and they do. All that data is useless and it's easy to torture and get any shape you want. This looks like the real data, and I'm going to show it to you. I'm going to show it to you right now. So we're going to stay on screen, and here I think everybody can see these are, everybody here understands the urban island effect. The urban environment contains, let me see, preserves heat overnight so that buildings and roads and airports and concrete and even lawns and gardens and neighborhoods trap the sun's heat during the day and release it very slowly at night so that you don't get the lows in a city that you would get out in the country for the same basic, climate area, the same basic region, you'd get much higher lows in the city and the real true lows out in the country. And so I've put together, and some people have seen, a list of the data from dozens and dozens. This is just a small sample of the remote thermometers that we can see. Here's from 1892. This is hundreds of thousands of actually, this is one. So this is just in Cooperstown, New York. So it's thousands and thousands of data points. And these are the highs. So we have what we see here when the up and down, this is summer and winter. These are the highs only. These are not the lows. So the high in summers are up here and the winter highs are down here. Okay. And what we see is not a heck of a lot of warming, right? Out if you go far enough from the city. Big Rapids Waterworks, Michigan, far from the city. You see some warm 30s. You see some cool 60s. It's actually got some heat in here in the 60s. And then, you know, nothing special, pretty flat. And this is raw thermometer data. And we could talk another time about whether raw thermometer data needs to be adjusted or not. Some of the time it does. Here is Bloomington, Indiana University, and it got more urban as the 60s, 70s, and 80s went on, but it's not a big change here. There was looked like a 2-year gap here for some reason. Don't know why in the 50s. That might have been the Korean War. Not sure. Here we'll go to Austin, Texas. Again, outside of town, and started early. This started in the 1880s. Again, this is all maximum temperature. So we see the winter's maximums down here. And yes, we had very hot 30s, the 1934, 36. These are very hot years. Summers, this is the Dust Bowl. So, you know, when things went down a little bit in the 50s and 60s, all right, up a little bit, sure. After 1990, the data is worthless. After 1990, forget thermometer data. It's worth nothing. This is California, out in the 200 miles from Los Angeles, started in 1900, and pretty good continuity here, missed a couple of years. But again, the 1930s were very hot. Here, the 1920s were very hot. The 30s were up here. We had a couple anomaly years in the 60s, mostly flat. We're not seeing what NASA wants to show us when they show us graphs of average temperature. We're seeing pretty flat. This is even a city. This is Atlantic City, New Jersey. This is guaranteed to have been more urbanized in here, and yet, you know, the temperatures really are pretty flat. Here we look at Bologna. Bologna is a nice weather station because it started in about 1850, taking measurements, and has solid contiguous. And this is very unusual for Europe because in most of Europe, you lose a couple of years during the war. So Bologna managed to keep track of temperature during the war. That's pretty impressive. Here's the 1880s, very hot, cool again in the early 1900s, 1930s and 40s, very hot in Bologna, down in the 60s and 70s, no surprise, and then up in the 90s. And here's the El Nino year here in 1998. But again, these temperatures after 1990 are worthless because this one actually might be pretty good, but the satellites tell the better story. And then here is Marseille, and they did lose a few years of keeping track. They started in 1920. They lost the war years, and again, hot in the 30s. There were some hot 40s, fairly cool, again starting to climb in the 80s. And again, this is all pretty much worthless, but it isn't growing much. It isn't that hot. Okay, and now to go quickly to the last, here we go. The last satellite era is 40 years long now, since 1979. And this is the latest. This is March. And what we see over the last 40 years is that we had the big El Nino in 1998. So no surprise there. You can kind of wash that out of the average. And we had a big one in 2016-17. So this was El Nino driven. This was El Nino, you know, it's about 11 years on average, but it's pretty variable. And then we have an El Nino now, but it's not nearly as big. So other things are happening here right now. This is real thermometer data. This satellite does not measure at 6 feet above the ground like the thermometers. It takes an average bulk temperature reading of about the lowest kilometer or so of the lower troposphere. It might be 2 kilometers of the lower troposphere, and averages all that together. It's a much better reading than anything on the surface, because measuring the surface from satellites is rife with error. Anything on the surface, because you're hundreds of miles up, if not thousands, and you're trying to take the difference of two small numbers. You know, and they're just the chance for errors of measuring sea level, for example, from satellites is useless. Sea surface temperature is mostly useless. These surface temperatures don't mean anything. What matters is the bulk atmospheric temperature. And so this is actually a pretty good measure of what's been going on. And what you see is, yeah, we're coming out of the last ice age. We're coming out of the little ice age. Of course we are. And we've got some El Ninos to poke through the average, but we've got some cold years too. And, you know, it all more or less is at a fairly even slope. And if you could take satellite measurements for the last 200 years, they would show a gradual, practically straight line slope over the last 200 years. They would show more or less the last 200 years, this, which isn't much. It's about 1 degree Celsius per 100 years. So maybe 2 degrees Celsius coming out of the little ice age. Thank goodness. Thank goodness for us. It's 2 degrees warmer than it was 200 years ago. And that's been pretty steady as far as we can tell since the early 1800s. All right, so that's sunspots and the contemporary record. I'm leaving out the last 2 or 3 years. I'll cover that another day. Any questions about the sunspots, thermometers, or satellites? There are competing satellites. You'll hear from NASA and from England. There's some satellite data, and they try harder to get that surface temperature, and it's much less accurate. It's much less meaningful. Their goal is to torture their data and show the dramatic rise that goes up with CO2. And they purposely depress temperatures in the 30s. And Tony Heller has shown this very well. They drop temperatures in the 30s and they accelerate temperatures in the last 30 years to show how amazingly correlated it is with CO2. But that just doesn't reflect reality. All right, so that's not bad. That was a 1 hour that I expected. I'm sure it was, I don't know, was it 80% too much, 20% too much? Was that kind of overkill?
I thought I just got my head around the obliquity precession and all that, but then you threw in the moving around, and I was like, oh no, everything's gone out the window. But I suppose with those 230 million year cycles, I mean, we probably don't even know, you know, what that does yet, because we have no records. It must just be theoretical in terms of how that affects things. Or, I mean, you said we've got the stuff in the rock, but what information that gives us about what the climate was, or.
The key, though, Joe, is that what drives temperature depends on the time window. And on a time window of the last 14 million years, what's driving, or 30 million years, is the shape of the continents, right? What's driving before that in a bigger window is probably some galactic influence, and mostly still the shape of the continents. And then you've got the atmosphere and the magnetosphere and a bunch of other things of the last, 500 million years. So a bunch of things. And then ozone had to build up, and then you know, the plant cover, a lot of things influence climate. But then on the order of the last 10,000 years, you can clearly see that precession is driving. But on the order of the last 4,000 years, precession hasn't changed much. You know, Polaris is more or less still the North Star, say for the last 2,000 years. So that's not a driver. Now we go to sunspots on this lower time scale, and sunspots, which have about an 11-year periodicity, do have a fairly significant influence, but there are many other factors. And so I'm not a big sunspot fan. I'm not spending a lot of time reading sunspot papers and watching videos of sunspot people because it's fascinating, but it's just not as direct and as forceful a driver for me, although there's definitely something there. And when you look at the little ice age driven by the modern minimum, you've got to say, oh yeah, watch out for those minimum sunspots. Those can be miserable. And possibly as we march our way up, we zigzag our way up through the next 2 or 3 groups of sunspots, we may hit some much warmer times. That's entirely possible.
Yeah, I was thinking, looking at the first graph, it looks like it was getting more chaotic, more up and down, but gradually colder. And right at the moment, it looks like we're on the top, like a hot bit. So if you go right back up to the top.
Well, talking about sunspots?
No, I'm going back to the first.
Well, that's going to
the
be on the
graph there.
order of tens and 20s of thousands of years. You know, this
Yeah, it's
precession-
like you said, when you zoom in, it just kind of seems like, you know, we're nearing a peak, you know, and after that it will, if anything, you know, that first graph to go off, we will be heading down temperature wise back into
the next thing from an orbital mechanics point of view is that precession's gonna swing the seasons around again, but that's happens in 12,000 years. So I don't know how much do we care about 12,000 years? I think, you know, what's
Yeah.
of more importance is how will the next couple hundred years play out. And that's entirely driven by 2 things: the sunspots, which is really the amount of sunlight coming in, and the ocean currents, which do almost all the work at the resolution of the last 100 years and the next 100 years is almost all ocean currents. And that's where we're going to go next. So, but you
Yeah.
can see that we've had a bit of a peak in sunspots, and that's going to come up again. We've got another group here waiting for us, and that could give us higher temperatures and more chance for the alarmists to run
that's what
headlines.
I'm thinking, sort of wishful thinking. It's going to start getting colder, but it's probably not. We're probably
It's
going
going
to
to go up and down. There's other reasons it could get colder, and for sure, we're going to come into another minimum Remember, this is the 70s, this minimum. So we're right around the corner from sunspots heading down again. And once again, in the next 20 years, it'd be very likely to us, you know, we can assume that this is a 65-year cycle that we're going to talk more about. So between the sunspots going down and the ocean cycles, I think we're going to see colder temperatures in the next 30 years. And we might not, but if you use history as a guide, I would say temperatures are probably going to go down in the next 30 years. Next 200 years is different. Now, if that's very confusing, which it certainly could be, you're going to get to watch this again. This video will be up later tonight. And everybody will be able to see it because I didn't do sunspots for the other group. So I hope that this is kind of a good self-contained 1-hour lesson that you can just scrub through and see, you know, pick what you want to watch again. The one thing I caution is that you'll see all kinds of nonsense on YouTube about this stuff. And almost invariably every Milankovitch video spends the last 20% of the video talking about CO2 and climate change from CO2. It was all this orbital stuff in the past, and now that's gone, and now it's just CO2. So you just have to just leave little comments like, you know, I don't know, if you leave enough comments, YouTube sends you a warning, and I've gotten that warning a couple times. So be careful. Censorship is alive and well at Google. But now we can have more of a conversation for the last 15 minutes, just about, we'll talk about CO2 and the greenhouse effect next week. I'm going to give you an assignment. I want to give everybody an assignment to read over the weekend. It's short. And we'll get into that. So just now we're kind of leaving the temperature series behind. Hi, doggy. And we'll talk more about CO2 next week. And then we'll get really into the ocean cycles and the heat pump, which is where the action is. And that's, the more you know about that, the more your conversations with friends will just, you know, make things worse, because they don't know anything about heat. And that, you know, lots of people, I mean, there's a lot of error by omission going on by saying this is the radiative balance. If you've seen my video on this, well, the radiative balance, you know, is showing that the heat is building up. Yeah, well, most of the heat goes through the oceans, and most of our climate is determined by the ocean. So sorry, you know, if, you know, why is Cape Town so warm, and why is England's climate so much warmer than Montreal's climate, so much warmer than, you know, Siberia's climate? They're all on the same latitude, you know, because of pressure systems, air and water pressure systems, and oscillations that move heat. That's why you can say, for example, that the Little Ice Age is proven by the Thames River freezing over. Well, it's proven because the Thames River froze over 26 times in 200 years. But that's not true. It doesn't prove a thing, because you could easily say that that London and the Thames is in a valley that has atmospheric effects that concentrate the cold at that time. And it could easily be that 100 miles either way or something, you know, it didn't freeze, right? So that's not a global effect, you know. And supposedly CO2 is a globally well-distributed gas. So if there aren't any more questions, I'll go into a little spiel on that. But please, I want to make sure and, you know, answer questions about galactic, solar. You know, we're traveling around the galaxy in a tilted plane, solar effects, and sunspots. Any questions about those things? Comments? You've got to, I'm just trying to bake in the idea that the driver of climate depends on the period of time you're looking at. Okay, Tony.
Yeah, I've got a comment about the sunspot effect in the Bronze Age, because in the UK, near to where I am in Derbyshire, what they call the Peak District, but also I think pretty much in Scotland, within a generation around the Bronze Age, people that were living on the upper moorland and the hilltops all moved into the valleys. So you see that
the Bronze Age.
Yeah.
It was horrible.
And the pressure on food, because your traditional farming methods were just completely gone.
You'd be lucky to survive that
Yeah.
300 years of death. Siobhan.
Yeah, just as a question, I thought your history lesson through the temperature ranges was quite good. And recently I was at some local planning thing and we were talking climate. And I was asking somebody there, I said, if humans can control climate, let's assume, I said, what would be the optimum climate for planet Earth anyway?
Yeah.
And because I've not seen any of those discussions.
Pre-industrial?
Quite interesting.
Really?
Yeah, well, not really. Well, I haven't. I'm not saying that they haven't happened, but
they want us to go back to pre-industrial temperatures in 1800.
Well, this is what I said. I said all the conversations I hear is about trying to return us back to what was just before the industrial age, which was a mini ice age.
Horrible.
But where is the discussion of what actually is the optimum. Yeah. So has anybody thought about that? Anyway, I was sort of told, oh, I don't know, but I'm sure the scientists will have thought about it and they'll have worked it all out. I did manage to stop myself rolling around the floor laughing at that point, but there we go. But yeah, I was just sort of thinking, so if humans can control climate, then why are we stuck with the idea it has to be the mini ice age? We could have it at any climate. So what is the best one, you know? So I use that as that usually stops conversations fairly well.
Maybe we should just vote and adjust the temperature according to the majority.
Yeah, we could do.
Scary thought. All climate reasoning is circular. That's where we are.
You sure it's not got a precession or an obliquity to it or anything like that?
It's crazy, because if you can adjust the climate, where do you want it to be? And where it is because we adjusted the climate, and that's because of CO2, which just goes around and around. There's no science.
Absolutely. Yeah.
It's scary. Yeah, Tony.
We've got quite a few examples of volcanic effects cooling the climate and disrupting agriculture. Yeah. So if you put yourself in a cooler starting point, you're heading for trouble anyway. You're much, and I'm not even going to go down the road of what they're proposing to block out the sun, but just natural effects are much more serious at a cooler temperature.
And we have no control over them. So whatever happens, happens. It doesn't matter what we do. Fortunately, government programs always fail. And so whatever they try to do to adjust the climate won't work, and it'll just be government boondoggle money grab, and that'll be the end of it. Won't have any effect, I hope. If they do manage to cool things, that would be pretty bad. The people from the Gates Foundation are here to help us. I will show another something else quickly. I'm saving this for a couple of weeks, but I want to do one thing. So let me run in here now. We kind of got through that. Actually, we got through it as when I thought, but there were fewer questions. But I'm sure there, I've been doing this for thousands of hours, so I expect that, it will be helpful for you to revisit this from time to time. And it's certainly explained in excruciating detail in Javier's books. But if you can watch this video again anytime you want. I want to, I'm going to go over this in other times, but I wanted to go over one thing. Not the no, somebody was just mentioned something that I wanted to. Well, I just came up with this recently. You hear all life ceases if CO2 drops below 150 parts per million. It's kind of the implied. Are you guys with me? Do you see maybe you don't see my screen? Hold on.
No,
I think you don't see my screen. So you hear all the time, all life will cease if we drop below 150 parts per million. Well, we know from studying the last 4.5 billion years that has never happened. The Earth came prepackaged with tons of CO2. Much of it is now locked up in rocks and turned into carbon. Calcium carbonate. Calcium carbonate was otherwise known as Europe. Jerusalem, the rocks of Jerusalem and the cliffs of Dover, it's all carbon, and that's all shell making. And so we've never been, not too long ago, somewhere around the I think it was the either the Dark Ages or the Little Ice Age was below 300 parts per million, and below I mean, sorry, below close to 200 and something parts per million in the little ice age. And we've never been down to 150. And it's true that all plant life would stop at 150. The planet has never, ever been there. All plant life stops anyway when it's cold enough, when you have, ice ball Earth. And before plants, there was a whole lot of cyanobacteria that was having a field day, and it was terrific for them. So the Earth is not trying to maintain life in a balanced range. The Earth is a piece of rock spinning around a star, and if something happens, it'll go far enough away to kill everything. The Earth has no problem with that. The parachute is not trying to save your life. It just depends, how it plays out. Okay, and so if for some reason there was enough shell making and enough precipitation of CO2 to get to 150, the Earth wouldn't care, and life would evolve, because we evolved to be in this range. So thinking, this is the circular reasoning, thinking that the Earth is here to keep us in this range is the opposite of what's really going on. We evolved to be in the range that the Earth is in, and if it goes out, we will have to evolve, because it can. It's just momentum, right? The Earth is slowing down. The sun is slowing down. The sun's day is 26 days long. It's slowing down a little bit. It's going to explode and take over the Earth in 500 million years. I mean, all this stuff is not designed for any kind of right temperature according to anybody. There is no right temperature. There's no right amount of anything. It's just the way it is. We can't do anything about it. We might as well enjoy it. Now, in 13,000 years, the glaciers will come back, and it won't be as bad, I think, as it was 13,000, in 20,000 years, I think that the glaciers will mostly come back, and this will be mostly driven by obliquity, and it won't be as bad. But a couple obliquities later, and we're talking about 46, 92, the third one or so is looking like it could be very bad. And there will be miles of ice again over the poles. This will not happen for thousands of years, but there will be. And by then, humans will still be around in 40,000 years. They'll 20,000, 40,000. They're going to have to deal with these ice ages. And it'll be interesting to see what technology they bring to this, because the ice is coming. But
I think maybe going underground might be the answer. Living underground, and then you're less vulnerable to the surface. It depends.
There's no way to imagine. I mean, we might be able to harness the power of the sun in all kinds of ways in 1,000 years. Who knows? We might build domed cities. I don't know. Yeah. Precession is likely to just go heat us up a bit in 13,000 years. So that's going to depend on the sunspots probably more than anything. But come back down again and give us a little more coincidence with obliquity, and we could have some very long glaciations. It's really all about glaciations, right? We're in an interglacial now, right? The Earth wants to glaciate because we're far enough from the sun, because we're round enough. Because we're round enough, the Earth wants to glaciate. So what we get is occasional times like now when the tilt of the Earth and everything aligns to beat back the glaciers, the ice, and we're lucky. And, historians will look back 200-300 years from now and say, well, they had a warm period and they squandered it. Things got cold again. So, and this is just another thing I wanted. Whenever something goes up, like temperature or anything, and I will talk about this in another time, but whenever something goes up that's more or less random and beyond our control, everybody feels like, well, we've got, this is our fault. We're driving this thing, right? And so when it goes down, they'll pick something else to say that we're driving. They'll sacrifice some other witches for some other, for some other thing. And right now they're selling indulgences to the church, because if you give enough money to the church, then the church will save us from the weather. This is all basically the same mentality, that you just have to give enough money and pay enough homage to the church and get out of the way and let them do, you know, their usual thing, you know, which is to take money and make things worse. So whenever some random variable goes up, they just grab onto that. Sea surface temperatures is perfect. Sea surface temperatures don't drive our climate. And if you're measuring them from satellites, it's meaningless. And we had, and I'm going to talk about this in a couple of weeks. We had a huge Hunga Tonga eruption 2 years ago that just managed to put more water vapor into the stratosphere than has been in the stratosphere for millions of years, maybe tens or hundreds of millions. It just happened to be the right depth and the right amount and the perfect type of explosion to put water vapor into the stratosphere. That was totally unpredictable. So we're just dealing with a bunch of stuff that when it happens, boom, this is money in the bank for us who can use it to our advantage, you know, to create industries off of this, you know, these random events to solve the problem. We're here to help. You can tell I'm really excited about government. Okay, we're wrapping up. Any questions, comments, rants? Yesterday we took on fluoride in the water, which I happen to think is a fantastic health intervention, and there's plenty of people who are very, very skeptical of that, but that's another story. Tony.
Yeah, I was just going to say that in terms of going into ice ages and really extreme climate change, parts of the Earth become apparently more hospitable. There's an idea that the Vedas, which is the Indian ancient text, because they talk about continual day, that the people that, or the tradition that preceded the writing down of that, were people that were living in the Arctic Circle at the time of the Ice Age. So,
well, during an ice age, no one was living at the Arctic. Do you mean during an interglacial?
It's at some point where that was before people moved south towards India. That's the notion. Somebody's written a book about it, an Indian guy.
Doesn't make sense to me. I'd need a lot more detail, because most of the
actual geology or the weather side of it. But in terms of history, what I'm saying is we may have less knowledge of where the most hospitable places were at prehistory time. So
maybe most of the people settling India came from the Middle East. So
this is a description of there being, you know, continual daylight and things.
I don't know. If there's a paper on this, I'd read it.
There's a book.
I'm not interested in books. I can't. It's just too much, because there's, you know, books, there's a million books. And Javier's book, you know, I've spent a lot of time. Pick your experts carefully. Javier is one of my experts. I have a few climate experts, and I have a few statistician experts, and I have a few economics experts, and I follow them because I know that they're reading the papers. I don't know, maybe. I'm not saying no. I'm just saying, not, you know, it's all about the details. Michael.
Hi, David. Sorry, I missed, what was the homework brief again?
I will give the homework. I'm going to upload it to the system. So you'll see it in the announcements. I'll announce it probably tomorrow. I got to keep writing it, but it's going to be about, the greenhouse effect. And I caution you not to watch any videos on YouTube about the greenhouse effect, because I haven't found one that I thought was any good.
Okay. So, and where do we see the upload? Just
I will announce it in the announcements and I'll press the alarm thing so everybody will get a ding. You know, you'll see it when you arrive, I think. And it will probably be under homework or something or assignments. I think there's an assignment section.
Okay, so yeah,
So
so
you
we
can-
got to log into the portal or a portal?
Oh, you're not logged into the portal?
No.
Right. Okay. So send me an email and I'll send you the invite. Okay.
All
You
right,
have my
brilliant.
email?
Yeah. I'll get your notifications.
Yeah.
Okay.
So yeah, I'm doing most of it through the portal. And that's where the videos are. So you'll see all the previous videos.
Okay.
So
Yeah,
that's
yeah.
important. Yeah.
Okay. All right, thanks.
Sure. Okay, I'll stop recording. And then anybody else has any other questions, that's fine.